Okay, so we will, again, just to remind you, talk today about normal mode expansion and electromagnetic field quantization in resonators. And typically in quantum mechanics or quantum optics classes, the problem that you will do as a toy problem for quantum optics is treatment of a free space resonator. So you have two mirrors and then you have vacuum in between, and you can actually treat all the problems where you have a uniform medium in the same way. But for the resonators that we're interested in this class, you cannot really treat them that way because they have non-uniform dielectric constant, as this photonic crystal resonator here shows. And for that reason, we have to go today through the treatment of electromagnetic field quantization in media that have non-uniform dielectric constant. So I'll just very briefly review quantization for just simple free space resonator, and then we'll move on to quantization of electromagnetic field and normal mode expansion in resonators with non-uniform dielectric constant. Okay, so what is the basic idea behind electromagnetic field quantization? And again, we have to go through this in order to talk about cavity quantum electrodynamics and light matter interaction next week. So we need to know how to quantize electromagnetic field. But the basic idea of the whole process that we'll go through today is that there is an analogy between classical harmonic oscillator and mode of electromagnetic field. So you have harmonic oscillator on the left, mass on a spring which oscillates, position of this mass, let's say, follows a function cosine omega t as a function of time, and then momentum from Newton's law would be proportional to time derivative of the position. So these two variables, position and momentum, are related to time derivatives. For electromagnetic field in a resonator, as shown here, but let's assume we have a lossless resonator, you will have some electric field pattern in space, and if that electric field varies in time as sine omega t, then magnetic field in time would vary as time derivative of electric field. They would be out of phase, right? So it would vary as cosine omega t, or in other words, is if electric field time dependence is given by some function q of t, then magnetic field dependence would be proportional to time derivative of q of t, which we will label as p of t, right? But the bottom line is that both electric and magnetic field oscillate as a function of time, and they're out of phase by 90 degrees. And if you look at these two pictures, you can already draw analogy between classical harmonic oscillator and electromagnetic field in a resonator. Basically, position and momentum that you have in case of a classical harmonic oscillator are pretty much analogous to electric and magnetic field in a resonator. And then potential and kinetic energy inside of a classical harmonic oscillator would likewise be proportional to energy stored in electric field and magnetic field. So total energy for a lossless system as a function of time would oscillate between electric field and magnetic field for a resonator, and also likewise for a classical harmonic oscillator between kinetic and potential energy. Okay, so that's kind of the cartoon picture and the motivation for all of this, but now we will quickly go through a review of a 1D cavity, which is just two mirrors separated by free space, by vacuum. And of course, if you have some uniform refractive index between the two mirrors, then it's the same problem. You just put an extra epsilon or n squared in Maxwell's equations and wave equation. But here we'll assume that we have vacuum in between, so permittivity of vacuum. And it's one-dimensional system, meaning that a field basically just oscillates in the z direction, the direction perpendicular to these two perfect mirrors. And we will pick certain direction for polarization of electric field in the XY plane, but that's all unimportant for the purposes of this problem. It's all one-dimensional. You just write the equation in one dimension. And this is the problem that you must have seen if you took introductory quantum mechanics or quantum optics. If you take any quantum optics textbook, it would start with a problem like this. So I will go through it quickly. There are more details in the course reader that is already online. And again, if you need, if you didn't take quantum optics or quantum mechanics before, then please let Raul know, and he will go in more greater detail through this particular problem in office hours. But in the interest of time, I'll go through it quickly and move on to the problems that are of relevance for this class. So again, going back to 1D cavity with free space in between, since we have free space, we can just write wave equation, Helmholtz equation for medium with a uniform dielectric constant. Here it is. And then we can solve it as any partial differential equation. You solve it by writing separation of variables. And here I'm trying to be precise in writing the whole procedure, just because we follow exactly the same procedure for all the other examples. When you have non-uniform medium, when you have other types of media that are analyzed in the course reader. So we also follow this wave equation, separation of variables, and use the same notation for time-dependent part and spatially dependent part. But of course, I'm sure that all of you know that in this case, field distribution would be a standing wave in the z direction. So what do we do here, right? So we have Helmholtz equation, we write field as a product of time-dependent part, spatially dependent part. We plug it back into the equation, wave equation, and from there we can decouple two equations for spatially dependent part and time-dependent part. Of course, spatially time-dependent part would have a solution which is just sine or cosine. We pick sine of omega t and label that time dependence as q of t for electric field. And then the spatially dependent part would have solution which is in form of standing waves. And here you have some function sine of k jz, where kj is equal to j integer times pi over L. L is the distance between mirrors, and j would correspond to the order of the mode we're exciting. So clearly we can fit some integer number of half wavelengths here, right? And then j would correspond to the number of half wavelengths that you're fitting between mirrors. Here we went also one step further in terms of normalizing the function. So we assume that all of the electric field between the mirrors is uniform, and mirror has area of capital A, which means that the volume is distance times area, where the field is non-zero. And in that case, you need to normalize the field by this prefactor in order to make sure that all of your normalization of the field is equal to 1 when you calculate the energy inside of the resonator. When you solve the field, you can check quickly for orthonormality, right? And orthonormality here means that product of the spatial distribution of two different modes inside of the resonator would be equal to Kronecker delta. And of course, it's Kronecker delta because we already have normalization, but for two different field patterns, it would be equal to 0. So that you can prove, and I think I believe in quantum mechanics, you prove by calculating these products of signs and actually calculating the actual integral of the product of signs. But here we will not really do that. It's easy to prove that that's indeed the case by going back to the wave equation and knowing that this wave equation has the form of the eigenvalue equation for the Hermitian operator, right? So if you have the equation in a form of a Hermitian operator, then you automatically guarantee that the solutions corresponding to different frequencies would be orthogonal to each other. And that's this equation here. Any questions about this? Okay, so if you have an orthonormal basis, then you can expand arbitrary field in the system as a superposition of these solutions, right? So we have mode J, which has time dependence Qj, that's just sine of omega Jt, and then some constant Cj multiplying that, and we assume that the electric field is polarized in the x direction. And of course, this is something that you've already seen before. It's just repeated with some notation that we will adopt to use later. So any arbitrary electric field in the system is a superposition of these different standing waves that you can have in the system. So here is our normal mode expansion for electric field. You can do exactly the same thing for magnetic field, but you can also just write that your magnetic field from Maxwell's equations is proportional to electric field via Curl equations. And then you will find that the magnetic field would have to be oriented in the orthogonal direction relative to the electric field. And the expansion would be given here. So if electric field follows the spatial pattern of sine kz, then magnetic field would follow cosine kz. If electric field has time dependence of q j of t, which is sine of omega t, then magnetic field would be cosine of omega t, which we label as time derivative of cosine of qj of t, okay? So you don't have to go through the whole process. You can just find this from Maxwell's equations. And just to make this simpler for you, we will write that this expansion coefficient in the field, Cj, which gives you a contribution of a particular mode in the field expansion, can be written as the square root of 2 omega squared, where omega j is the frequency of a particular mode, divided by V, that's the volume of the whole space, defining a resonator, epsilon naught, permittivity of vacuum, and Mj. Mj is an artificial constant. It doesn't really, mean much, but we will introduce it to establish analogy between this mode of electromagnetic field and harmonic oscillator easier. So Cj gives you a contribution of a particular mode in the expansion. So if you, for example, only have mode 1, then C1 would be non-zero and all the other C's would be 0. But that also means that M1 would be non-zero. You can always find constant Mj, which is related to the constant Cj from this relation. And you'll see how this helps you figure out why this is exactly a harmonic oscillator. Any questions? Okay. Yeah, go on, please.
Can the C term, like the weight of the mode, be related to the energy in that mode?
Yes, that is exactly what it is related to. And that's also why I'm introducing this constant Mj. You'll see, so to draw analogy between energy in electric field and potential energy or kinetic energy. Yeah.
Okay, cool.
Okay, yeah, so you see it in a moment. It's an artificial constant, but of course, once you have Cj, you can find Mj, right? It's easier to write it that way. So of course, electromagnetic field energy is the integral of electric and magnetic field energy density. And you can plug in expressions that we have here, right, and calculate the total energy. And when you do that, you will obtain something that looks like this, right? So all the steps in between are also in the course reader, but we can just go back to the previous page and you will see why this is the case, right? So for each individual mode, energy in electric field would be proportional for electric field to Qj squared, right? And then Cj squared, and Cj squared is proportional to M omega squared, right? So that's related to Jason's question, right? So energy in electric field is directly proportional to M omega squared, and also likewise for the magnetic field, but there are some additional constants that will cancel some of the prefactors that we picked here. Okay, so energy in electric and magnetic field are proportional to this constant Cj squared or Mj. When you're calculating energy in the whole electric field, you of course have to square this whole expression. But since individual modes are orthonormal, then all the cross terms will disappear when you integrate them over a resonator. So total energy in electric field is the energy, sum of the energies in individual modes, because you started from the system of orthonormal modes. Does that make sense? Right? Because integrals, right? When you square this and integrate over the whole resonator, all the cross terms would vanish, right? They would be basically products of sine kj1z times sine kj2z, but we know from orthonormality that has to vanish. So you basically lose all the cross terms, right? And you just have contributions of individual modes, and those contributions of individual modes can be written in this particular form. So can you recognize which one comes from electric field, which one comes from magnetic field? Here. Yeah, electric field is proportional to Qj of t, right? So this term has to come from electric field, right? And then prefactor there, C squared would be proportional to M omega squared, right? So this comes from contribution of the mode J electric field. And then for magnetic field, we introduce Pj of t, which is proportional to time derivative of Qj of t times this constant Mj, right? So that's what basically, I mean, we just renormalize the time dependence, and that puts the energy in the magnetic field in the form of Pj squared divided by 2mj. All the cross terms where J1 and J2 are mixed, they drop off. That's because of the orthonormality of the field inside of the resonator. And sum of the energies in all of the individual modes gives you the energy in a resonator. So again, here I skipped kind of few steps in between, which is just simple math, but all the important parts are there. So energy in electric field, electromagnetic field is the sum of the energy in electric field and in the magnetic field. Okay, so if you look at this form here, what does it remind you of? this total energy. How does it look like? Let's go back to the first term. How does this look like? P squared over 2m. What's that?
Looks like kinetic energy.
That's kinetic energy, exactly. And the second term looks like
Potential
energy for a harmonic oscillator, right? Except that this P is not exactly momentum and Q is not exactly position, but they are related via relation, the same relation as momentum and position. P is m times Q time derivative, right? So Q is analogous to position, P is analogous to momentum, and this M is kind of analogous to mass, although of course it's not mass. It's some constant that defines the contribution of a particular mode in the expansion, right? We didn't really introduce any new physics. I mean, of course you can calculate total energy for electromagnetic field inside of this 1D resonator. We just tweaked it a little bit with some normalization constants to write it in the form that right away looks like the energy of electromagnetic field inside of a harmonic oscillator. Does that make sense, right? And then contribution of a particular mode is contained inside of this constant mj. Okay, good. So, you know, going back to this, now we can just easily draw analogy between mode of electromagnetic field and harmonic oscillator. I mean, mass on a spring is a harmonic oscillator, but so is electromagnetic field inside of a resonator, right? So total energy for a harmonic oscillator is kinetic plus potential energy. You've seen this expression for a classical harmonic oscillator, I'm sure, and you know that from Newton's laws that momentum is mass times time derivative of position, right? So this is your kinetic energy, this is your potential energy. Likewise, for a mode of electromagnetic field inside of a resonator, you can write total energy as energy in electric field and energy in magnetic field, where these time dependencies describing how magnetic and electric field vary in time are related with something that is analogous to the relation between momentum and position. So here, the energy in magnetic field kind of looks like your kinetic energy term in harmonic oscillator, and energy in electric field looks like potential energy term, right? And P and Q are like momentum and position. So complete analogy here. So if you write classical harmonic oscillator, what are the variables that describe it? We have position, momentum, frequency, and mass, right? For mode of electromagnetic field in a resonator, we have Q of T, Qj of T for the mode J, which is basically analogous to position. It's not position. We know that it's basically time dependence of that mode. Then we also have Pj of T, which is analogous to momentum. Again, it's not a momentum. It's proportional to time dependence of the magnetic field, right? And we know that it's a conjugate variable relative to Q of T. So they're related via this Newton's law. And then omega frequency of a harmonic oscillator, classical harmonic oscillator, is analogous to omega j, which is frequency of a mode in electromagnetic field in a resonator. And then m mass for harmonic oscillator is analogous to mj, which is this constant that we introduced proportional to Cj, which describes the contribution of a particular mode in the electromagnetic field expansion. Does everybody see analogy here? Okay, so that really tells you why we introduced mj, right? If we didn't introduce mj, we would have two terms. And of course, you can still prove that, you know, all of these relations and Hamilton's equations are satisfied. But when you see them this way, it's obvious that this is a harmonic oscillator, right? You don't really need to prove anything. So, which is why we try to re-normalize it in the right way. So then, you know, this is telling you that each mode of electromagnetic field is basically like a harmonic oscillator, right? So each mode of a resonator is a separate harmonic oscillator. And you want to pick the modes that are orthogonal to each other, because then, you know, when you're calculating energy of the system, you will lose all the cross-coupling terms. You will have system of independent harmonic oscillators. If you didn't do that, then you will have some coupling between mode J1 and mode J2, which means that your harmonic oscillators would couple in some way. And we don't want to do that, right? That makes things complicated, which is why we started from Hermitian Operator and started from orthonormal modes and made sure that we can actually express them as independent harmonic oscillators. So how did you quantize harmonic oscillator in quantum mechanics? So this is a very brief review. I'm sure that you probably all of you have seen it, but I'll just very quickly go through it in 2 pages. And for the purpose of doing quantum optics, we absolutely don't care how the wave functions of harmonic oscillator look like. That's totally unimportant. The only thing that we care about is how the Hamiltonian looks like, and we'll express it in terms of annihilation and creation operators, and we also care about how electric and magnetic field operators look like. But all the wave functions of harmonic oscillator, we don't care about it, right? So here is quantization of a harmonic oscillator, right? So in harmonic oscillator, we have position x of t, momentum p, and we have energy. So this is classical, classical world on the left, and in quantum mechanical world on the right. What we do? Well, we introduce position operator x, momentum operator, which is proportional to gradient, right, in space. So these two are basically coming from conjugate variables. So it's minus I h bar d per dx. Position and momentum operators do not commute. Commutator is I h bar, right? And you probably also seen this previously in quantum mechanics. So x and p do not commute. And then total energy can be expressed as p squared over 2m plus m omega squared x squared over 2. And this is exactly the same as the expression for total energy, classical total energy of a harmonic oscillator, except that you substitute operators instead of position and momentum. You substitute position and momentum operators, which makes this energy operator, Hamiltonian. So then you can actually go from here and calculate wave functions of harmonic oscillator. We don't care about that, right? This is really not important for quantum optics. What we will do instead, we will express the Hamiltonian in terms of annihilation and creation operators. And to get there, you have to go through one extra step of introducing normalized position and momentum operators. So those are these x hat and p hat. This is not introducing new physics, just normalizing position and momentum operators. And then you can write the whole Hamiltonian as h bar and then normalized Hamiltonian, which would be x hat squared plus p hat squared. And these normalized position and momentum operators also do not commute. Commutator is I. And then once we have these normalized operators, we can introduce new operators, A and A dagger, which are superpositions of x hat and IP hat. Here they are. And once you have those, it's easy to show that x hat squared plus p hat squared can be simply expressed as A dagger A plus 1/2. Actually 2A dagger A plus 1. But then you can actually go back to the Hamiltonian and write the whole thing as h bar omega A dagger A plus 1/2, right? Because this x hat squared plus p hat squared is proportional to product of A dagger and A, right? There are 2 options here. Typically, when you quantize harmonic oscillators in quantum mechanics, you just stick to your position and momentum operators, and you find your wave functions, and you don't even need to worry about A and A dagger. In quantum mechanics, in quantum optics, we prefer to work with annihilation and creation operators because they have important meaning and important action on the system, and they're called annihilation and creation operators, as some of you know, because they would basically annihilate a quantum of energy or create a quantum of energy in the system. And they would raise you or lower you down the ladder of eigenstates of the system. So we will not really work with position and momentum operators because they're meaningless. Instead, we will work with the Hamiltonian, which is expressed as A dagger A plus 1/2 times h bar omega. And this is also Hamiltonian of a quantum harmonic oscillator, but again, we prefer to work with A and A dagger, which describe everything instead of position and momentum, which are not real position and momentum in case of a harmonic oscillator. Any questions? Yeah, go on. Yeah.
So you mentioned like several times that the wave function is not important in quantum optics. Could you give us a simple reason?
Because these wave functions of position and momentum, right? I mean, the eigenfunctions, the actual position and momentum are not really position and momentum. They're just analogous to position and momentum here. It's not true that the wave function is not important. We will actually do use and describe wave function of a photon as a function of space and time. But that's not the eigenfunction of space and position that you would obtain by solving this particular Hamiltonian here.
So basically you are more interested in things going on in Fock space instead.
Yes, yes, absolutely. And, you know, you do describe wave function, and, you know, it's related to also distribution, classical distribution of field in the system, as we'll see later. We're just saying that this X and P here, I mean, or Q and P that we will have for quantum optics are not real position and momentum, right? So the treatment that you had when you found the solutions of this Hamiltonian in real space for a quantum harmonic oscillator are not really relevant here in quantum optics, because this Q here would not really be space anymore, right? It's just an analogous variable to that. Okay. So then how do you quantize field, right? So we quantize Hamiltonian, right? This is not surprising because your electromagnetic mode is analogous to a classical harmonic oscillator. So then in quantum regime, it would be the same as a quantum harmonic oscillator. So Hamiltonian would be just A dagger A plus 1/2 times H bar omega, right? So that's not surprising. But you need to introduce additional operators, and those additional operators that you need are electric and magnetic field operators. So how do you quantize the field, right? So for a 1D cavity, you just need to go back to the solution of the electromagnetic field and plug in the right types of operators, right? So here is your classical solution of the field, right? So we had Qj of t, Pj of t, which describe time dependence of electric and magnetic field, and Wj, which is the energy, right? So what do we do here, right? So for our electromagnetic mode, Qj of t would be replaced when you quantize the system with some operator, Qj, right? Remember, this was analogous to position, and this is analogous to position operator, but it's not really position, right? So we introduced this as to describe time dependence of electric field. Pj of t is proportional to time derivative of Qj of t. Again, this is all classical on the left side, which means that when you quantize, since there is a relation between P and Q, which is the same as the relation between momentum and position, after quantization, they will follow you will introduce a new operator for Pj, which a momentum operator, which would be related to position space via this gradient, or it would be equal to minus IH bar d per dQj. So it's the same story as for quantum harmonic oscillator, except that you are replacing, you know, momentum space with Pj and position space with Qj, but these are not real momentum and position. These are just two variables that are analogous to momentum and position. And of course, since operators are introduced in this way, then the commutator between these two operators would also be equal to IH bar, same as for position and momentum. Because you can even prove that because they're defined in exactly the same way as position and momentum operators for harmonic oscillator. And what is important to emphasize here is that those commutation relations hold for one specific mode of the system. When you look at two different modes of the system, their operators are all commuting, right? Why are they commuting? They're commuting because you started from independent harmonic oscillators. They're operating on completely different spaces, eigensubspaces. So for one specific mode, when J is J prime, Q, P commutator is IH bar, but for two different modes, they're all commuting because you started from orthonormal basis, and that makes your life much easier. And then energy, classical energy of the mode J was defined as sum of energy in electric field and energy in magnetic field. And at the very end, we wrote them in this form that resembled energy of a harmonic oscillator, kinetic and potential energy. Now to go into a quantum regime, we just substitute operators instead of P and Q, right? So this would be total operator for the energy of a mode J inside of a resonator. And then we can keep going, right? Introduce also normalized Q hat and P hat the way we introduced X hat and P hat. Those two would also not commute. And then we can express Hamiltonian in terms of this X H hat, normalized Hamiltonian. H omega would be in front of that, right? So it's represented in terms of Q hat and P hat squared. And what would be the next step? What do you think? What did we do for a harmonic oscillator? Did we stop at X and P for Hamiltonian, or we did something else? Instead of using position and momentum, what can you use to represent Hamiltonian?
Creation and annihilation.
Creation and annihilation, right? And how would you introduce them? As a superposition of position and momentum operators, right? But we have these analogous position and momentum operators, so it would be Q hat plus IP hat or Q hat minus IP hat. I mean, here I basically just copied 2 slides that I showed for harmonic oscillator, just rewrote them with Q and P. Once you establish analogy, it's exactly the same procedure, right? So you introduce A and A dagger as superpositions of Q hat and P hat. Here they are, and then you don't really need to work with position and momentum anymore. Your Hamiltonian is represented as A dagger A plus 1/2 times H bar omega for particular mode J. And then the total Hamiltonian, since you can have a lot of different modes in the system, would be H bar omega J, which is for the Jth mode. And then all the creation and annihilation operators are also defined for a specific mode, right? So you add up Hamiltonians for each of the modes in the system. So the bottom line is, resonator is not a harmonic oscillator. Each mode inside of this resonator is a harmonic oscillator, okay? And you can have infinitely many modes. If you start with orthonormal bases, they will all be independent harmonic oscillator. The oscillator is described in this way, and each one of them is described with a Hamiltonian for a harmonic oscillator, because for each mode independently, energy would oscillate between electric and magnetic field. Okay, so far we just have a Hamiltonian, right? So here is our Hamiltonian, H bar omega, A dagger A plus 1/2. This is Hamiltonian of a harmonic oscillator. And you probably know for quantum mechanics, that you can have eigenstates of this system and you can find energy eigenvalues. Again, we will not look at the spatial distributions of the eigenfunctions because they're meaningless here, but we will just label all of the energy eigenstates in the Dirac notation as n, right? Where n is the number of energy quanta in a particular energy eigenstate. So n would be an eigenstate of the Hamiltonian corresponding to n quanta of energy in the system, and energy of that state would be H bar omega n plus 1/2. So when you draw all of these eigenstates for a harmonic oscillator or for a mode of electromagnetic field, which is also quantum harmonic oscillator, they would form a harmonic collider, which means that they're separated by H bar omega. And ground state is 0, which means no quanta of energy. The next one would be 1, the next one would be 2, and the nth one would be n. The ground state energy is H bar omega over 2, which is vacuum state, right? So you have no excitation in the system, but that's still energy is H bar omega over 2. And then all of the subsequent states are separated by H bar omega, which is energy of a single photon, right? You cannot really add quarter of H bar omega, right? Here, eigenstates are just separated by H bar omega. And these energy eigenstates of quantum harmonic oscillator or in mode of electromagnetic field are referred to as Fock states or photon number states. And they're referred to as photon number states because each one of these states has well-defined energy, right? If you're in the state 2, you know that you have exactly 2 excitations in the system, which we call photons, right? If you're in the state 1, you have exactly single photon, single excitation in the system. And if you're in the state 0, you have 0 excitation. You're in the vacuum state. Is that making sense? And this ladder of energy eigenstates for harmonic oscillator is called harmonic ladder. And harmonic means that all the energy eigenstates are separated by the same amount. And we'll see that there are also anharmonic ladders next week when we start doing light matter interaction. Okay, so we know that each mode of electromagnetic field classically is analogous to harmonic oscillator, classical harmonic oscillator. We went through the process, we reviewed quantization for classical harmonic oscillator, and by analogy, we quantized the field for a mode of electromagnetic field, which is also quantum harmonic oscillator. So Hamiltonian is H bar omega, A dagger A plus 1/2, right? And energy eigenstates, which are eigenstates of that Hamiltonian, would be just states with precisely defined energy, which we in quantum optics call photon number states or Fock states. State n would have n photons inside of it, precisely defined. There are 2 more important operators to introduce, right? So in classical electromagnetics or optics, we solved for electric and magnetic field in the system, right? And we have the solutions for electric and magnetic field inside of this resonator. But once you go to quantum optics, electric and magnetic fields have to be represented with operators, the same way that as energy becomes an operator. So how do we introduce operator for electric field and magnetic field? This is very simple. And again, I'm sure many of you have seen this. This is what we do. We start from the solution for electric field. This is classical solution for electric field, which we expanded in terms of the mode J. So that's what we did at the beginning of the class. And remember, Qj of t is the time dependence for mode J, sine kjz was the spatial dependence for the mode J. And this term up front came from normalization, because we normalized all the modes so that they are forming orthonormal bases, okay? So then when we quantize the system, we basically have to introduce operators. And instead of this Q of t, which was analogous to position inside of, in a classical solution, it was analogous to position inside of the harmonic oscillator, we introduce operator Q, okay? And then your operator describing electric field is given here. So what is important to note is that the spatial dependence of electric field is preserved. It's still there, right? So electromagnetic field that you solve classically is still there. There is an operator that is replacing your time dependence of the field, or the variable that was analogous to the position. And instead of keeping Q operator, which is kind of meaningless here, not particularly useful because it was analogous to position, but it's not really position, we will represent Q in terms of annihilation and creation operators. So you remember that we also introduced Q hat, which was a normalized version of Q, right? So we can do that here in the next step. And then instead of Q hat, we can write Q hat as A dagger plus A, so sum of annihilation and creation operators divided by √2, okay? So that's clear from here. When you add up these two expressions, you have A dagger plus A divided by √2, and we can write that here. And this gives us operator for electric field, which is represented in terms of annihilation and creation operators, which have more meaning in this system, but you can actually see that spatial dependence of electric field is preserved through the whole process. And these combinations of constants up front that we have, all of the constants, we will label as some amplitude EJ. And you see that that amplitude is square root of h bar omega divided by V epsilon naught. Okay, so what does this mean, right? If you have electric field which is completely uniformly distributed through volume V, which is volume of a resonator, what would be the energy of the field? Electromagnetic field. It would be epsilon, right? If you had amplitude EJ, it would be epsilon times EJ squared, right? Divided by 2 times volume V, and that would be for electric field, and the same thing for magnetic field, which means that the total energy would be epsilon naught times EJ squared times volume V, correct? So if you had field which was completely uniformly distributed through the volume V, and you had only exactly energy of a single photon inside of that mode, which is h bar omega, that mode would have an amplitude of EJ. So that's the meaning of this prefactor here, right? EJ, normalization factor, comes from basically uniformly distributing a single quantum of energy, h bar omega, throughout the whole volume of a resonator. So if you have a smaller volume of a resonator, this prefactor is larger and your electric field operator is larger, which is telling you already telling you why you want to minimize volume, right? If your volume of a resonator is smaller, this prefactor is larger and the operator is larger. And since this operator plays a role in light matter interaction, then the whole interaction between electromagnetic field and your atom or artificial atom will be stronger. Of course, when you don't have the free space resonator, then you will have something different here, optical mode volume that we introduced earlier. We'll see that later, but the bottom line is the same, right? So always this prefactor in electric field operator would be obtained by uniformly distributing one photon of energy throughout the whole volume of the resonator or electromagnetic field in a resonator. Is that making sense? Okay, so how do we find magnetic field operator? What do you think? what would we have here, right?
Could take the cross product, use the Maxwell equation.
Yeah, so you take the curl equation to find magnetic field, right? And then you will have here something like cosine kz, right? Which would also be preserved in the operator. And instead of q of t, you will have time derivative of q of t, right? Which we labeled as p, right? So you just do that, you know, you go back to your expression for magnetic field, which you find from Maxwell's equations. This is a classical solution. There is spatial dependence, which depends on cosine kz, and there is a time dependence pj of t, which basically comes from time derivative of q. And then you substitute instead of this to find operators. You introduce your p operator, which is equivalent to the momentum operator, right? Your spatial dependence is still there. Then you can use p hat operator instead of p operator. And then instead of p hat operator, you can write it as a minus a dagger divided by √2, right? And here it is. And then this prefactor EJ is again one photon uniformly distributed through the whole volume of a resonator, exactly the same thing that we had for electric field. Okay? So these operators are Hermitian. They're equal to their Hermitian conjugates. You can actually easily prove that. Same thing for energy. So the energy has real eigenvalues, right? And these operators, we'll see what their meaning is and how we will use them. Just as a side note before we move on to the next part, some textbooks express all of these field operators in Heisenberg picture. We used Schrödinger picture. Schrödinger picture means that time dependence is not in operators, but it's basically in your eigenstates of the system, in the states of the system. So here you see there is no time dependence, right? But you can equivalently express them in the Heisenberg picture because the Heisenberg picture representation of annihilation and creation operators has these extra terms e to the minus I omega t and e to the plus I omega t. So if you express your operators, field operators in Heisenberg picture, this is how they would look like. And then from your states of the systems, from wave functions, you will remove your time dependence. You will have them in the operators. This is just as a side note so that when you see that in quantum optics, it's not confusing you. And we already emphasized that for one particular mode, annihilation and creation operators do not commute. A dagger is one, but for two different modes, they would commute because you started from completely independent harmonic oscillators that are orthogonal to each other. So commutation would hold. So AJ prime dagger for J and J prime, which are different, would be equal to 0. Few, again, more notes before we go to non-uniform medium. Electric and magnetic fields now, when you quantize the field, are not variables anymore. They're operators, right? Same thing as with energy. Since they're operators, you can, of course, find their eigenstates. You can also find their expectation values for a particular state of the system. So if your optical field in the system is represented in terms of some state psi, then the expectation value for electric and magnetic field can be calculated using these inner products, right? Or between psi and electric or magnetic field operators applied to psi. So you cannot really talk about values of electric field and magnetic field anymore. Once you quantize the system, you can talk only about expectation values of electric and magnetic field for a particular state of the system. Okay, does that make sense? And since your electric and magnetic field operators depend on space, when you calculate these expectation values, there will be spatial dependence. So what would be the meaning of this expectation value? The meaning of the expectation value would be that if you are measuring the value of electric field inside of certain resonator at different positions, the expectation value that you will obtain in that experiment would be given by this particular expression for a particular state of the field. Now, the question is, what is the state of the field? What's psi here? What can psi be, right? Psi is some state of the system, which you can represent in terms of the eigenstate of the system, right? We know energy eigenstates of the system. So psi can be represented as some superposition of eigenstates of the system, right? So psi, for example, could be a Fock state where you have precisely defined number of photons, or it could be some superposition of Fock states. And depending on what superposition you have, you can have a variety of different states of electromagnetic field, right? You can have non-classical states of light or quantum states of light, such as Fock states, right? Or you can have also classical states of light, such as coherent states. So here is just a very brief review of that, right? Energy eigenstates of the system are Fock states. So in the previous expression for the expectation value of electric and magnetic field, you can write that psi is equal to any Fock state n and calculate the expectation value of electromagnetic field. But you can also write some superposition of Fock states, and one special superposition that we care about is a coherent state, which is a superposition of Fock states bit coefficients that follow Poissonian statistics, right? So for a coherent state with mean photon number n hat, the coefficients in the superposition of Fock states, energy eigenstates, would be following Poissonian statistics, okay? Which means that if you have a coherent state of light, number of photons is not precisely defined, but instead the probability that you have some number of photons nk would be given by Poissonian statistics, magnitude squared of the coefficient up front. Okay. So just to review that for those of you who haven't seen it in quantum mechanics, and again, everything we did so far is probably a review for many of you, yeah, but we have to go through it quickly before we move on to what we really care about here. So laser is a classical light source, which produces Poissonian statistics of light at the output. So light at the output of a laser is not in an energy eigenstate. Right? It doesn't have a precisely defined number of photons. If you take a Tice sapphire laser where you are producing pulse every 13 nanoseconds and you measure photon number per pulse, this is what you would see. You maybe see 2 photons in the first pulse, 1 photon in the second pulse, 4 photons in the third pulse, and so on. It's not constant. And the number of photons that you will see would be given by the Poissonian statistics. The probability that you have n photons in each pulse would follow Poissonian statistics with the mean photon number n hat, which depends on your power setting on the laser. So if you crank it up, then mean photon number is larger. If you crank it down, mean photon number is lower, but you will never have precisely 1 photon at the output. And if you measure what we call statistics or second order correlation function, for this output of the laser, this is what you would see. You will see series of peaks, equidistant peaks with the same height that are separated by 13 nanoseconds, repetition period of this laser. And this second order autocorrelation function is basically given by this expression. It's an expectation value of the expression that depends on annihilation and creation operators, but it's an intensity correlation measurement on the system. So you basically do intensity correlations, and it's not surprising that they peak at the intervals that depend on the repetition period of the laser. But all the peaks would have equal height. If, on the other hand, you produce something like a single photon source, which has as the output precisely Fock state, 1 photon at the output, right? Then the autocorrelation function would not look like this. And the way to measure autocorrelation function is this setup, which we call Hbt setup, or Hambury, Brown, and Fish type setup, where you send your beam, you divide it by a beam splitter, and then send it into 2 detectors. So this measurement for a laser was obtained exactly using this, right? So if you take a laser beam, you take it here, you split it on the beam splitter. Of course, these 2 beam splitters would produce coincident clicks at time intervals that are separated by integer multiples of the repetition period of the laser. And all of those coincident clicks would have equal height for integer multiples of 13 nanoseconds. If you produce a source of Fock state 1, right, you produce exactly 1 photon per pulse and you send it to this setup to measure second order correlation function, what will you see? Well, this photon cannot be split on a beam splitter. It would go here or here, right? So can you ever have coincident clicks of these 2 detectors? No, right? So that in the scheme of this setup here, of this measurement, will you have a peak at time delay 0, right? So peak at time delay 0 would mean that your detectors click at the same time. right? But that's never possible for this particular system, which means that second order correlation function would have the central peak missing, but you still have side peaks because there is nothing wrong with detecting one photon at the left detector at time 0 and another photon at the right detector at time 13 nanoseconds times integer multiple, right? In reality, of course, it's not completely missing. Often you would see that central peak, which is still there but suppressed, which is what we call sub-Bosonian light. It's still non-classical light. And this is, for example, an actual measurement on single photon generation from a quantum dot, where central peak is 4% of the side peaks, which means that you have suppression of multi-photon probability to 4% of the Bosonian source. Okay.
Sorry,
Yeah, please.
Could you like explain a little bit on the equation? I couldn't actually imagine it as a second order coincidence.
Yeah, so we don't really have enough time, or maybe we can actually set it up outside of the class to discuss greater details, but you can see that these are intensity correlations because A dagger A, right? A dagger A is proportional to Hamiltonian, right? Or energy is photon, basically photon number operator. So if you're doing it, A dagger A at time 0 and A dagger A at time tau, which is all in the numerator of this expression, that means that you are doing expectation value of the having certain photon number at time 0 and some photon number at time tau, right?
Yeah, exactly. Yeah.
Exactly. So if you are doing that, right, and you have a single photon source, then obviously you cannot really have one photon at time, two photons at time 0, right? Because tau converges to 0, right? Which means that this goes to 0. But you can have one photon at time 0 and one photon at time 13 nanoseconds times n, right? Which means that this peak would exist at integer multiples of 13 nanoseconds. Does that explain it? Okay.
Yeah.
Yeah. But of course, you know, there is more to it than this. This is just like intuitive picture for now, right? And of course, for coherent source, that's all fine because you can always split it, right? And you will have also finite probability of measuring at time 0. Okay, so now I will give you a very brief break, but before we make a brief break, I would like to just summarize what we did so far, right? And then we'll move on to resonators. And again, sorry for having to go through this quickly, but we have 1 week class this particular quarter. So we figured out this would be the best part to take out and we'll address it in the office hours. If anything is unclear, and usually this is the part of the course when, you know, some people have background, some people don't have background, please let us know and we will teach it separately outside of the regular lectures. But let's summarize what we did, right? So to quantize the electromagnetic field in a general resonator or general electromagnetic system, we just follow the same procedure that we saw for 1D resonator, right? So you do normal mode expansion, you solve the problem classically. You can do it for electric field, and you can find magnetic field from electric field from curl equations, right? You can calculate total energy. You recognize parameters P and Q that are equivalent to position and momentum, to momentum and position, right? And together with energy, they satisfy Hamilton's equations. Or in other words, you can write energy in electric field and magnetic field in the forms that are analogous to kinetic and potential energy. Once you do that, you can introduce equivalents of position and momentum operators, P and Q, and they can be represented as superposition of annihilation and creation operators. And then you basically quantize the system exactly the same way you did for harmonic oscillator. And when you quantize electromagnetic field, that means that you represent energy operator, Hamiltonian, the same way as the operator for harmonic oscillator. So A dagger A plus 1/2 times H bar omega. And then you also have to introduce operators for electric and magnetic field. Those are the 3 things that you care about, okay? So now we did that for 1D resonator. And if you take any quantum optics textbook, that's where it stops. It just does free space or 1D resonator, right? Because until 15 years ago, pretty much all of the light matter interaction experiments were done in resonators where you have 2 mirrors and vacuum. And that's still kind of workhorse platform for most of atomic physics experiments. People didn't really care that much about non-uniform dielectric constant in the side of a resonator. That was not an issue. But for the systems that we're discussing here, we do care about it because we have photonic crystal resonator, and photonic crystal resonator is clearly not 2 mirrors with vacuum in between. So we need to see how we quantize the field in that system And then we can actually do light-matter interaction in that system. So the issues to address in the rest of the class today, and probably beginning of the class on Tuesday, is how to handle medium with non-uniform dielectric constant. Because most resonators are not just free space, which is handled in the introductory quantum optics classes. And we've seen that from the example of photonic crystal resonator, right? You have a lot of holes inside of some slabs. So how do you handle that? How do you represent that? How do you pick normal modes of the system? How do you separate them into independent harmonic oscillators, right? So that's your normal mode expansion. And then how do you establish analogy between that and harmonic oscillators to quantize the electromagnetic field? So I'd like to make a brief break. Maybe we shrink it to about 2 minutes or so, 2-3 minutes, and then we move on to medium with non-uniform dielectric constant, which is basically the same as arbitrary resonator in a lossless case. If you have any questions, happy to answer, of course. Yeah.
I just have a naive question on why it's called normal mode expansion.
Because you are expanding it into modes that are orthogonal to each other, right? So they're normalized and orthogonal, which means they're orthonormal, and people call that normal mode expansion.
Oh, okay.
Yeah, so you're expanding, I mean, normal mode expansion means that you are expanding electromagnetic field classically into a system of modes that are orthonormal. And the way to assure that you are doing that is that you write your wave equation as an eigenvalue equation for a Hermitian operator. If you do that, you know for Hermitian operators, eigenstates corresponding to different eigenvalues are orthogonal, and you can always normalize things, right? And then for degenerate modes, you don't guarantee, of course, that they're orthogonal, but you can always normalize them, right? You can always pick in that subspace normal basis. So normal mode expansion means you basically find system of classical solutions of electromagnetic field that are orthonormal.
And you didn't consider any degeneracy.
If you have degeneracy, then you have to pick in that subspace orthogonal modes, right? But you can always do that, Gram-Schmidt orthogonalization, right? You picked eigenstates and you orthogonalize them to each other.
Yeah.
So that was trivial for the case of free space, right? Because Helmholtz equation is right away, it's just Laplacian, right? Or second derivative for one-dimensional case, which right away gives you eigenstates that are orthogonal to each other, right? Like in the problem that we had. Problems occur when you have something with non-uniform dielectric constant because wave equation is different, and that's what we'll be doing now. But you can still make sure that you write your wave equation in the form of eigenvalue equation for Hermitian operator and solve it. So that's what we'll be doing now, right? So starting with Hermitian operators always helps because you guarantee that you have orthogonal modes, and then you don't have to worry about coupling between different modes when you're calculating total energy of the system, which would be converted to coupling between different harmonic oscillators. That doesn't mean that you can't solve the problem if you don't have orthonormal basis, right? That you can always expand in a basis that's not orthonormal. But when you do quantization, you should start from orthogonal modes, because it makes your life much easier. Okay. All right, so maybe we continue since we don't have too much time. And again, I know that if maybe some of you need a little bit more time to process what we went through, but it's probably a review for many of you. So if you have any questions, let me or Raul know. So for the treatment of resonators, in this class, it's important to address one more question. What happens when you have non-uniform dielectric constant? And that's not treated in quantum optics books for the reasons we just discussed, because that's not how people used to do experiments. But all the new types of resonators, even those used in atomic physics, have non-uniform dielectric constant. So what do we do there, right? Well, we can still write Maxwell's equations. I mean, here are Maxwell's equations. But the difference is that epsilon can vary in space, and we assume that material is non-magnetic, it's mu naught. But now, instead of having divergence of E equal to 0, as would be the case when epsilon is uniform, we can only write the divergence of D is 0, and D is epsilon E, right? And because of this, you cannot really write wave equation using Laplacian, right? Because curl of E would not, you cannot really cancel gradient of divergence of E minus Laplacian E when you expand this. No, you have to keep it in this form, right? Because the divergence of E is not 0, which means that you cannot simplify curl of E with Laplacian. Does that make sense? Right? And I'm sure you've seen that identity for curl of E. It's in every single electromagnetics textbook, right? So how do you write wave equation for the system? Well, you just, again, apply curl to one of the curl equations, you combine it with the second one, and here is your general wave equation for this particular problem for electric field. Or you can do the same thing for magnetic field. But what's the way to solve this equation, right? So you start from this partial equation, the same way that we did for 1D resonator. You try to separate variables, so we can write our electric field as a product of spatially dependent part and time dependent part. I write time dependent part as eta of t and spatially dependent part as f of r, and you can successfully separate variables here. That's not a problem. Time dependent part would give you just simple second order differential equation, like this is sine omega t, cosine omega t, right? Not surprising. I mean, omega is separation variable. And spatially dependent part would give you this equation. Not Laplacian anymore is what you had for free space. Instead, you will have 1 over epsilon curl of something. So that's the operator O. And your spatial distribution of the field is eigenfunction of the operator O. Okay? So the problem that we have when the electric constant is non-uniform is that this operator O that we have here is not Hermitian. And you probably remember from quantum mechanics or from math that Hermitian means that when you're calculating inner product between arbitrary function A and operator applied on the other function B, that operator can jump from one to another function in inner product and the result stays the same. That's not the case here, and it's not the case because it's not really a symmetric operator. If this 1 over epsilon was in between curls, it would have been fine. Or if epsilon was constant, it would have also been fine. But here we have this epsilon, which varies in space, which is outside of curl of E. So when you're trying to prove that operator is Hermitian, and you have that in the course reader, as you're slowly moving curl from one function to another, epsilon will be trapped under the curl. And you can see that you're actually obtaining different results. So if operator O is not Hermitian, that doesn't mean that there are no solutions for the field. You still have solutions for the field, which are described with functions f times eta. But what does this mean? This means that I cannot say anything about orthogonality of solutions corresponding to different frequencies, as I could when there were solutions of Hermitian operator. You agree with this? Right, so that's what this means. That doesn't mean that system is falling apart. Just I can't really say anything about its solutions. So there are a few options here. One is to work with magnetic field operator, which we already looked into when we were solving the variational principle in quantum mechanics. Fortunately, it's Hermitian, so you can work with magnetic field. But the problem is that we actually need electric field operator more than we need magnetic field operator, because we're looking into light matter interaction, and it's basically electric field operator that matters more because it's a dipole, electric dipole interaction that matters in majority of the systems. So you can go to magnetic field and then find magnetic field operators and go to electric field operators from that, or you can actually do something to this operator for electric field to make it Hermitian. And there is a way to solve that. I mean, I prefer that approach. It's the approach proposed originally by Roy Glauber and Lowenstein in 1991. Roy Glauber is also the person who developed theory of photon statistics. I mean, this is why those second order correlations are called G2. It's because he introduced them in his paper. G is short for Glauber. And he was a professor of physics at Harvard until recently. So the approach that they proposed, and which I prefer, is just to fix the operator for electric field. And what they do is very simple thing and beautiful thing. Instead of writing it in this particular form, solution for the spatial field pattern for electric field, this f of r, can always be written in terms of some other functions g of r as g of r divided by square root of epsilon of r, right? So you kind of just introduce another set of functions, g of r, which are proportional to solutions of the operator O, but they are also multiplied by spatial distribution of the dielectric constant, or square root of that. And if you go back to the eigenvalue equation for the operator O, you can rewrite it in terms of these functions g, right? Every f that we have is g divided by square root of epsilon. So when you go back here, you can write it that and plug in g divided by square root of epsilon instead of f, you have this equation here, okay? And this equation here can also be seen as the eigenvalue equation for an operator O1, which is everything that you have on the left-hand side other than g, and eigenfunctions of that operator are functions g. Does that make sense? So we didn't do anything. We just introduced new set of functions by multiplying these functions f by square root of epsilon and rewrote the eigenvalue equation.
But even if you solve G perfectly, and then you can demonstrate G can be decomposed into orthogonal bases, then our ultimate goal is to solve what is E's decomposition.
Absolutely, absolutely. But you know, I think that's an excellent question, Yushu. I think you're already seeing where we're going. So operator O1 that we have here, which is 1 over square root of epsilon curl of 1 over square root of epsilon, it's easy to show that it is Hermitian operator, right? Because instead of having epsilon outside or trapped inside, it's kind of split outside. So when you're moving curl slowly, then this first epsilon would be trapped under the first curl, and then another curl, and then there will be 1 epsilon left. So you are actually starting with symmetric form, and it's also shown in the course reader if you're interested in the proof that this is Hermitian. So what that means is that O1 is a Hermitian operator, and that tells you what? That tells you that G's are eigenfunctions of a Hermitian operator. So I can't tell anything about F, but I can tell about G's, right? That G's are orthonormal if they correspond to different omegas, and that omega squared is real. And keep in mind that that's the same as the frequency of a mode, it's the same omega, right? So I can say that omegas are real and G's are orthonormal. But if I can say that, then I can say a lot about F's as well, because F's are related to G's, right? But it's not a traditional orthonormality. So what I can say, right? So, and look at course reader for a proof that O1 is Hermitian if you're interested. So O1 is Hermitian, right? G's, which are eigenfunctions of this operator, are orthonormal. Automatically, I don't have to prove that. That's a consequence of hermiticity. Omega squared is real, that's frequency of the mode. And G's are orthonormal, which means that they satisfy orthonormality as normally defined in math. But since each G is square root of epsilon times F, right? I can just write square root of epsilon times F here and rewrite the orthonormality for G's in terms of functions F. Which means that, not surprisingly, right, F's are eigenfunctions of an operator which is not Hermitian. So they are not orthonormal, but they are, using this trick, we see that they are orthonormal in this special way, right? And what is a special way? Special way means that you have an extra epsilon under the integral. And that extra epsilon actually makes a lot of sense because F is a spatial distribution of the field. So what's epsilon E squared? Energy in electric field, right? Because this here for G's is just orthonormality that we have in math. This here is telling you that you have normalize energy in each mode, right? Physically, it has much more meaning. But, you know, I like this approach because it's much more beautiful. And of course, if you have functions G, which are eigenfunctions of the operator O1, and operator O1 is Hermitian, that means that they're orthonormal, and you can expand arbitrary solution of an operator O1 in terms of superposition of G's, correct? Right? But that is also telling you that you can expand your arbitrary electric field as a superposition of F's, because you can expand arbitrary square root of epsilon times E, right? That's the space that for which G's are orthonormal eigenfunctions. You can expand arbitrary square root of epsilon times E in terms of G's. That's what the operator O1 handles. But that means that you can also expand arbitrary electric field in terms of F's, which are G divided by square root of epsilon. However, you have to keep in mind that these eigenfunctions that you're using for expansion are not orthonormal anymore in the traditional sense that we use in math. They're orthonormal with an extra factor of epsilon that we have. Does that make sense? Yes, so that's basically the idea. And this is, if you're interested in details, again, there is a paper from a while back by Glauber, but that's what we're doing. So basically, the bottom line is when you have a medium with a non-uniform dielectric constant, and most of the resonators that you'll treat have to be treated that way. It's not just free space between mirrors. Electric field can be still expanded in terms of these normal modes. You have time dependence, you have spatial dependence, contribution of a particular mode, but these spatial dependencies are not solutions of a Hermitian operator. So they are still normalized, orthonormal, but they have this changed orthonormality relation where you also have an extra factor of epsilon. And that comes from that trick from that where we kind of use the operator O1 that has eigenfunction G, which is Hermitian, to get to this relation. So, and this is already kind of telling you that when you are doing electromagnetic field quantization for this system, you need to normalize electric field in such a way that you have the energy in each mode normalized separately, right? Which is what we did also for a free space resonator, but we'll also do it for this particular resonator. Okay, so we have 5, yeah, go on, please. Any questions? No, okay. So before we stop, I'd like to just make a few more mentions, right? Keep in mind, right, we're expanding electric field in terms of this spatial field distribution F. So these are eigenfunctions of that non-Hermitian operator, but we proved that they are normalized using this special orthonormality relation, right? How do you normalize, right? So when you take an arbitrary resonator and you solve for electromagnetic field distribution, you will get electric field distribution for different modes in a resonator, okay? So can you just take directly that electric field distribution from your electromagnetic solver and plug it here and that would be your F? You can't really, right? You have to normalize it so that this particular relation is satisfied, okay? So if you take electric field from your arbitrary electromagnetic solver, so this is spatial field distribution, it turns out that you can just find F's by normalizing that electric field distribution with square root of mode volume that you find in the same way that we defined it before as integral of epsilon E squared over the whole volume of a resonator divided by maximum of epsilon E squared times maximum of epsilon E squared, right? So maximum of electric field energy density. So you run your electromagnetic simulator, you obtain electric field distribution. That's not normalized. That's not normalized to satisfy this particular relation, right? So then you just take it and you normalize it with square root of this mode volume times maximum of epsilon E squared. And it turns out that what you obtain exactly satisfies this relation. That's very easy to show because when you multiply mode volume by maximum of epsilon E squared, you just have integral of epsilon E squared, right? So then here you would have square root of integral of epsilon E squared and then integrating F times F conjugate epsilon gives you again another integral of epsilon E squared. So the result is 1, okay? So basically the bottom line is take unnormalized field and divide by square root of the mode volume defined in this way times maximum of epsilon E squared. And then you will obtain the right F's that are normalized in this way, okay? And this, everything in the denominator is just the same constant that you use to divide every single field at each point inside of the resonator. It's just normalizing the field everywhere. It's not really changing electric field pattern, but it is telling you how you need to normalize in order to satisfy this orthonormality condition that epsilon F squared is equal to 1. And this is also already telling you, I mean, some of you may have seen already this mode volume or square root of the mode volume inside of Purcell factor or some other factors defining light-matter interaction. This is exactly where it comes from, right? Because when we do quantization of electric field, we start from the normal mode expansion. Normal mode expansion for us means that you expand in terms of Fs, but they have to be normalized before you start doing quantization, and they have to satisfy this particular normalization, which means that you cannot just take whatever result of simulation you have from your electromagnetic simulator. You have to also divide each point, field in each point, with the square root of the mode volume times maximum epsilon v squared. And this will propagate into Purcell factor and light matter interaction, which is telling you that it is important what size of the mode volume you have. If you have a smaller mode volume, then this prefactor will be larger, and that prefactor will also propagate to electric field operator. In the same way that it propagated to electric field operator inside of the free space resonator, right? We also had square root of h bar omega divided by V times epsilon naught, except that there V was physical volume of the resonator. We assumed that field was uniform everywhere. But here field is not uniform everywhere. Instead of that physical volume, you have a mode volume. Does that make sense? Okay. So then it's very easy to show that gives you the right type of normalization. And then your normal mode expansion or electric field expansion, if you just take arbitrary field solutions from your electromagnetic simulator, would be expanded as follows. So you have contribution of a particular mode, you have normalized field, which is this square root, and then unnormalized field, and eta of t, which is time dependence. And we're doing this for lossless resonators only. We didn't do it for lossy resonators. So once you expand field in terms of these normal modes, which is what we already did, I mean, and it also holds for resonators, and now I'll stop at this one and we'll pick up from here next time. It is easy to show, I mean, using exactly the same procedure. Once you have normal mode expansion, you can identify, you can write the energy in electric field, energy in magnetic field, identify what's analogous to position, what's analogous to momentum, introduce position momentum operators, annihilation and creation operators, and so on. There are a lot of pages of detailed derivation inside of the chapter that we uploaded today, if you are interested in that, but you also don't have to worry about it. I mean, I know it is, we went through it for one example, which is 1D resonator. It's exactly the same story, except that you have to tweak expressions a little bit to establish analogy a little bit better. But once you do that, following the same procedure, you can find Hamiltonian and electric and magnetic field operators for this system. Not surprisingly, Hamiltonian will be just Hamiltonian for harmonic oscillator, right? Each mode is a harmonic oscillator. And electric and magnetic field operators, for electric field operator, you will have the form given here, or you can write F in terms of unnormalized field. So I'll write only electric field operator because I care only about that one for the purpose of teaching the next chapter. But here is how electric field operator would look like. And it is very, very similar to the one that you had for free space. It will have annihilation operator, creation operator. It's Hermitian, right? Because it's equal to its Hermitian conjugate. What's EJ of R? EJ of R is just electric field pattern, classical electromagnetic field solution. So that's preserved there. Spatial field distribution is preserved, and it's normalized by the mode volume. Okay? So previously for free space resonator, we had h bar omega divided by V mode times epsilon here. Here it's a little bit different, but it still is the same story. This is increasing as you squeeze field into a smaller volume, and spatial dependence of the field, classical solution of electromagnetic field, is preserved in the operators. So we'll pick up from here next time and then introduce Jaynes-Cummins Hamiltonian and also look into the interaction between atom or artificial atom and the field. But we had to know how to write operators for electric field in order to do that. Okay? So sorry for holding you on a few minutes longer, but we had to catch up because of the missing week. Thank you folks a lot, and I'll see you on Tuesday.
Thank you.
Thank you, bye. Bye-bye.
Goodbye.